stretch a spring, let go, and everything about the motion that follows is already written in a single curve, where the object speeds up, where it stops and turns around, where it can never go at all. One parabola encodes it all. Today we learn to read that curve, the energy diagram. Start with the force. A spring displaced from its natural length pulls or pushes the object back. So the spring force is a restoring force. Choose coordinates with the equilibrium position at the origin. Then x measures the displacement from equilibrium. The spring is stretched when x is positive and compressed when x is negative. The force law reads F equals minus kx, where k is the spring constant. Stretch it and the force points in the negative x direction. Compress it, and the force points in the positive x direction. Either way, the minus sign drives the object back toward equilibrium. Potential energy comes from the work the spring force does. The change in potential energy is minus the integral of the force component from the initial position x sub I to the final position x. Substitute the force law minus kx and the sign flips. The integrand becomes plus kx. Integrating kx from x sub I to x gives 1/2 kx squared minus 1/2 kx sub I squared. So the potential energy difference is 1/2 k times the quantity x squared minus x sub I squared. Stretch or compress the spring and the stored potential energy grows with the square of the displacement. The direction doesn't matter. Now compare the result with the first fundamental theorem of calculus. The theorem says the change in u from x sub I to x equals the integral of its derivative du dx over the same interval, but we just computed the same change as minus the integral of the force component. Two integrals equal for every choice of endpoints, so the integrands themselves must be equal. The derivative of the potential energy equals minus the force component, or flipping the sign, the force component equals minus the derivative of the potential energy with respect to position. Force is the negative slope of the potential energy curve. That one line is the key to everything that follows. The reference point is ours to choose. Set the potential energy to 0 at the equilibrium position, so u at 0 is defined to be 0. With x sub I at the origin, the difference formula collapses to a clean function. U of x equals 1/2 kx squared. Now run the new relation backwards as a check. Differentiate. The derivative of 1/2 kx squared is kx, and the force is minus that, minus kx. We recover exactly the force law we started from. Integrate force to get potential energy. Differentiate potential energy to get force back. Now draw the picture that carries the rest of this story. Plot potential energy against position. 1/2 kx squared is a parabola opening upward with its minimum at the origin, where the potential energy is 0. The units on both axes are arbitrary. The shape is what matters. Far from equilibrium on either side, the stored energy climbs steeply. Near the bottom, the curve flattens out. The exact bottom is fixed by calculus. A minimum occurs where the first derivative vanishes. Du dx equals 0. For the spring, the derivative of 1/2 kx squared is kx, and kx equals 0 only at x equals 0. Because force is the negative derivative of the potential energy, a vanishing derivative means a vanishing force. Check against the force law. Minus kx evaluated at x equals 0 gives 0. At the minimum, the net spring force disappears. The object can rest there forever. That point is the equilibrium, and every feature of the motion that follows comes from this shape. Here is why that equilibrium is stable. Near a minimum, the potential energy curve has positive curvature. It bends upward on both sides. Displace the object to a small positive x. There, the slope of the curve, du dx, is positive, so the force minus the slope is negative. It points back toward the origin. Now compress the object to negative x. There, the slope is negative, so the force is positive. Again, it points back toward the origin. On both sides of the minimum, the force opposes the displacement. That is the signature of a stable equilibrium, a valley in the potential energy with restoring forces on either wall. Add motion to the picture. At any moment, the mechanical energy E is the sum of the kinetic energy K and the potential energy U. Suppose the spring object system loses nothing to friction or air resistance, then no mechanical energy leaves the system, and E stays constant for the entire motion. It is a constant of the motion, one number that characterizes everything. With our 0 point at equilibrium, both K and U are never negative, so E is positive or 0, and E equals 0 only in one situation, the object at rest, sitting at equilibrium. Now put the energy on the diagram. For a positive value of E, draw a horizontal line at that height across the graph. The line is horizontal because E is constant, the same value at every position. This line intersects the parabola at exactly 2 points, at minus x max on the left and the plus x max on the right, setting 1/2 kx max squared equal to E, and the solving gives x max, the square root of 2E over k. Those two positions are the maximum compression and the maximum extension of the spring. We call them the turning points, and the motion lies entirely between them. The diagram now shows the kinetic energy too. Rearrange the energy equation K of x equals E minus U of x. On the graph, that difference is the vertical gap between the horizontal energy line and the parabola. Read it at a glance. At the origin, the gap is widest, so the object moves fastest there. Climbing either arm, the gap shrinks and the object slows. And at the two turning points, where the line meets the curve, E equals U, so the kinetic energy is exactly 0. The object stops for an instant, then the restoring force turns it around, and the story runs in reverse. Nothing is lost, so the motion repeats endlessly, a bounded oscillation between the two turning points. Read straight off the diagram. The turning points also mark a boundary. Look at any position beyond them, x greater than x max or x less than minus x max. There, the parabola rises above the energy line, so U of x exceeds E, and the kinetic energy K equals E minus U would have to be negative, but kinetic energy is 1/2 mv squared. It can never be negative. No object with this energy can ever be found there. These are the classically forbidden regions, and the allowed motion is confined to the interval between the turning points. One footnote from the frontier. In quantum mechanics, energy diagrams for quantum systems look remarkably similar. A potential curve, an energy level, the same geometry, but there is a very small probability that a quantum object can be found inside a classically forbidden region. A classical object never crosses that line. A quantum one occasionally does. The forbidden region is forbidden, classically. Step back and read the finished diagram. One curve, one horizontal line, and the entire motion decoded. The slope of the curve gives the force with a minus sign. The minimum is the stable equilibrium where the force vanishes and the restoring forces guard both sides. The height of the line is the conserved energy. The gap between line and curve is the kinetic energy, largest at the bottom, 0 at the turning points that bound the motion. Beyond them, nothing, classically. Before solving a single equation of motion, the energy diagram has already told you the whole story. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.